Hello my friends, welcome to another Cynic video. In this one we're going to be looking at energy changes and specifically the first part of this topic, so exothermic and endothermic reactions, what they are and how to draw reaction profiles for these two. Check out our other video on how to calculate energy changes and a second video on how what chemical cells and fuel cells are, which is only chemistry only or separate sciences only. One of the key principles in science is that energy has to be conserved. Whether it be in collisions or in reactions, it cannot ever be created or destroyed. So if we have a reaction where we take A and B and we go to make C, C might have less energy than A and B did in total. But that's because it's lost energy to its surroundings. So perhaps it's burning petrol using oxygen and we're releasing lots of heat as a result. So that's an example of an exothermic reaction. It's taking heat away from the molecules and giving it to the surroundings, so heat is exiting. And another example might be where we have X plus Y goes to make Z. In this case, Z might have more energy than X and Y combined. We haven't magicked energy from nowhere, it's taken energy in from the surroundings. So X and Y have taken energy from the surroundings get colder because it's an endothermic reaction. Therm or heat is being taken in to the reaction. So exothermic and endothermic reactions are two categories of reactions that happen in chemistry, and they happen in biology. Every single type of chemical reaction is one of these two. So endothermic in biology would be, for example, photosynthesis. It's taking energy in the form of light. In exothermic, respiration is an example because heat is exiting the reaction. So exothermic in chemistry, we define it as where we're transferring energy to the surroundings and the temperature of the surroundings increases. And good examples of that are hand warmers or self-heating cans. In both cases, you crack a bar or a bag, and as a result, two chemicals will mix or more, and as a result, they will react and release energy to the surroundings, getting the surroundings warmer. In endothermic reactions, they're taking energy in from the surroundings, so as a result, the surroundings get colder, the temperature gets decreased. And good examples of that, again, are things like ice packs or injury packs in sport. If you've got an injury, again, you crack open a bag and as a result, a reaction's triggered which takes heat away, cooling things down. And there are two more which you can look at in chemistry, which are thermal decomposition, where we're heating a chemical or a molecule or whatever to try and decompose it, break it down into two other or more products. And another example is in sherbet, which you've all done, I'm sure, in your mouth, where you take citric acid and you also take something called sodium hydrogen carbonate. And when they are in your saliva, they react together, taking energy away from the surroundings, your mouth, and make your mouth cooler, and it makes it feel funny. It's a nice sweet because of that. And all of this endothermic and exothermic idea can be investigated. It's required practical number 4, where you're investigating the variables that affect temperature changes in reacting solutions. So an acid plus metal reaction, you could vary the type of metal that you're reacting, or the concentration of the acid, or the starting temperature of the solution. So many different things you could do, and I'm not going to go into loads of detail about that because that kind of gets covered in the rates of reaction topic later on. But what I do want to highlight here is that in this reaction you need to make sure you're doing it in an insulated container because you want to minimize the heat loss to the surroundings. So using an insulated cup, for example, and a decent analog thermometer, or even better, a digital thermometer, which has a higher resolution, would be very good and very recommended. Now, we like to make science simple, so making things visual is a good way to represent ideas. And reaction profiles are exactly that. A reaction profile is a graph, a visual way of representing how much energy has changed in a reaction. So on this axis, on the x-axis, I'm going to put the progress of the reaction. So as the reaction happens and time goes on. And on the y-axis, I'm going to put the energy in molecules, because we're going to look at just the energy in the reactants and in the products. And so for both of these graphs, I can draw the reactants on first. Let's do it nice in the middle. This is how much energy the reactants have as molecules, because they contain chemical energy stored, don't they? So these are the reactants. And in an exothermic reaction, these reactants, as they react, will release energy to the surroundings. So the products are going to end up down here somewhere. The products have less energy than the reactants did. And in an endothermic reaction, it's the opposite. So the reactants take in energy from the surroundings as they're reacting, and the products end up having more energy. So they're higher up. So that's a good start point. That shows us the energy change in these reactions. If we draw a line here, we can show the energy change in an exothermic reaction is negative, and the energy change in an endothermic reaction is positive. So the products have gained energy in endothermic and they've lost energy in exothermic reaction. But that doesn't show the true picture, the full picture of a chemical reaction, because for a chemical reaction to occur, the particles have to collide. So in a gas or a liquid or with a solid, and they need to collide with sufficient energy. So if you think of these particles in a gas that are reacting together, they're whizzing around, they might bump into each other, and the reaction will only happen if they bump into each other with enough energy. And the minimum amount of energy they need to collide with to successfully react is called the activation energy, and we sometimes label that EA. Big E for energy, A for activation. And so when we're looking at, for example, burning glucose, the standard biology reaction with oxygen goes to make CO2 and H2O. When we do that, we're actually using the activation energy to break up the bonds in glucose and oxygen, and then when they reform to make new bonds, they release some energy again. So for an exothermic reaction and for an endothermic reaction, they both have to have an increase to a peak in energy, and this increase in energy that we need to give the reaction first is this activation energy. And it's the same for an endothermic reaction. They both go up to a peak first, and compared to the reactants, that's what we call EA, the activation energy. But in an exothermic reaction, when the new bonds are being remade, so when the products are being formed, like in this reaction for respiration, the reformation of bonds releases more energy than was taken in to start the reaction. So the energy level in these molecules goes down way further than the amount of reactants. And for the endothermic, again, we've got here the amount of energy that's released is less than was taken in to begin with. So the products end up, they've taken energy in from the surroundings as part of that activation energy. They've taken energy in and they've held on to that. They've released some, but not all of it. And so the products therefore have more energy than the reactants did to begin with. And these questions for drawing these profiles tend to be 4-mark questions. And so the marks are these. First is drawing the reactants and the products and labeling them and having them at the appropriate point. So exo, the products are below the reactants, and in endo, the products are above the reactants. That's number 1. Number 2 would be having this nice curve drawn, showing the energy change in the reaction. The third mark would be for showing what the energy for activation energy is, with an arrow from the reactants up to the peak. And again, over here up to the peak, that's the third mark. And the fourth mark would be from the reactants line down or up to where the products is. And that would be the fourth mark, having that drawn on and labelled. Simple. It's a really nice, easy question and a very common question. I would really expect this kind of question to come up in your tests and your mocks and in your exams. And that's a 4-mark question. So that's a quick overview. Do check out our other videos for how to calculate energy changes. And also, if you're doing separate sciences, look at chemical cells and fuel cells. Do like, subscribe and hit the bell for more videos that come out in the future. Thank you.